Hello guys, geometrical isomerism is continued. This is type 7, geometrical isomerism in allenes. Now first question is, what is allene? Compounds with consecutive carbon-carbon double bonds are known as allenes. Compounds with consecutive carbon-carbon double bonds like this, consecutive carbon-carbon double bonds like this. These compounds are known as allene. Now, what are the conditions for the allenes to show geometrical isomerism? The condition is allenes with odd number of double bonds with terminal carbons containing individually different units will show geometrical isomerism. Look at here. Allenes with odd number of carbon-carbon double bonds. This is very important. Odd number of double bonds with terminal carbons containing individually different units will show geometrical isomerism. Look at here. This is carbon-carbon double bond. 1, 2, 3. This is odd number of carbon-carbon double bond, consecutive carbon-carbon double bonds with individually different units. Here is A, here it is B, here D and D. Of course, this A will not equal to B, and of course this D will be not equal to E, and this one. So this is the condition of allenes to show geometrical isomerism. Now, look at the structure here. Look at here. The compound I have made is CH3 here. CH3, carbon, double bond, carbon, double bond, carbon, double bond, carbon. This is, say, hydrogen, and this is your CH3, the trans molecule. This one. Look at here. This is the molecule. Carbon, double bond, carbon, carbon, double bond, carbon, carbon, double bond, carbon, and hydrogen over there, methyl over there, methyl here, hydrogen here. This is the molecule allene with 3 double bonds, that is consecutive odd number of double bonds. Look at here. In this molecule, the carbon, look at here, the carbon here is sp hybridized. And of course the carbon here is sp hybridized. These two carbon are actually sp hybridized. So what is happening here? Look at here. This carbon is sp, this carbon is sp. So say for example, this carbon is S and P. Say is s orbital, that is 2s orbital of carbon, and say 2pz. These two orbitals for the sigma bond formation. These two orbitals for the sigma bond formation. So this sigma, this one is sp hybridized, this bond is sp, this bond is sp, this bond is sp, and look at here, the pi bonds here, the pi bond form is say px, and this one must be px. So this is your px orbital, this is your px orbital, and if this pi bond is formed by the overlap of px orbital, this pi bond must be formed with the py orbitals like this. So the pi orbitals over there and the pi orbitals over there are in the perpendicular plane. As a result of that, this hydrogen, methyl and hydrogen, that is bond 1, 2, 3, 4 exist in the same plane. What happens here? Look at here. These two p orbitals, pi bonds, and these pi bonds are in perpendicular plane, and the result of that, this one is perpendicular to this one, and this one is also perpendicular to this one. As a result of that, 1, 2, 3, 4, these 4 bonds becomes in the same plane. As a result of that, this molecule will show geometrical isomerism. If there would be the even number of double bonds. Look at here, in this molecule, if there is 2 double bonds like this, like, look at here, if there are odd number of even number of double bond containing compounds like this is even number of carbon containing compounds. So these 2 bonds and these 2 bonds be present in perpendicular plane. So this is your group A, this is your B, A, this is B, and this is D, and this is E. Then this molecule will not show geometrical isomerism. This molecule will not show geometrical isomerism because now if there are 2 double bonds, these 2 bonds and these 2 bonds are in perpendicular plane. Look at here, this one is like this is one A, this one is B, say this one is D, and this one is E. So these 4 bonds are in perpendicular plane, so this molecule actually show optical isomerism. We will learn later. This is a chiral axis. There is a presence of chiral axis. This is known as chiral axis. Due to the presence of this chiral axis, the molecule will show optical isomerism but not geometrical isomerism. So the condition of geometrical isomerism is it must contain odd number of double bonds and terminal carbon containing individually different units. Okay, this part will be discussed later. Now back to our matter of concern. Look at here, there are 1, 2, 3, 4, 5. Again, whatever be the nature of the D and E and A and B, the molecule will show geometrical isomerism. Of course, A and B and D and E will be different. Now this compound contain 1, 2, 3, 4, 5 double bonds. So definitely A, B and D, E, these 4 bonds lie in the same plane. So this molecule of course will show geometrical isomerism, and same condition will be applied. Then that is A and B will be different and D and E will be different. Okay, the next molecule, this one is C3O2 carbon suboxide, the protonated form of carbon suboxide. This is protonated form of C3O2. This is the protonated form of C3O2 carbon suboxide. C3O2 is O double bond C double bond C double bond O. Look at here, there is also carbon consecutive double bond, 1, 2, 3 odd number of consecutive double bonds, and oxygen contains 2 different groups. One is lone pair, one is hydrogen, and here oxygen contains hydrogen and lone pair. So this molecule will show geometrical isomerism. The protonated form of C3O2 will show geometrical isomerism. Okay, this is all about geometrical isomerism involving allenes. Let us start geometrical isomerism in fused bicyclic ring systems. Okay, the condition is in fused bicyclic ring systems, geometrical isomerism occurs about the bond joining the 2 bridgehead carbons. This is the condition. Let's take some example. This is our molecule decalene. This molecule can also be written in this way also. This one is trans, hydrogen, this hydrogen, these 2 hydrogen are actually trans, and these 2 hydrogen, and in this molecule these 2 hydrogen are actually Cs. This is your trans decalene, and this molecule is cis-decalin. Look at here. Here, these two hydrogen, the hydrogen atoms attached to the two bridgehead carbons are actually trans, and here the hydrogen attached to the two bridgehead carbons are actually cis. Now, look at the structures. This molecule, this is actually trans-decalin. Look at here. This is your view. Okay, this molecule is trans-decalin. What are the hydrogen atoms attached to the two bridgehead carbons? These two are bridgehead carbons because with these two carbons the two rings are attached. So this is bridgehead carbon. Look at here. These two hydrogen, this one, these two hydrogen are in trans position. So this is known as trans-decalin. And of course, the cis-decalin is, this is the molecule of cis-decalin. Look at here. It is written in this fashion. It has many conformations. Okay, this one. Okay, look at here. This is your cis-decalin. This is your cis-decalin. The hydrogen atoms attached to these two bridgehead carbon are cis. Look at here. This is your cis-decalin. This one. It is written in this fashion. These two hydrogen 1 and 2, these two are in cis position. And in trans-decalin, these two hydrogens are in trans position. These two hydrogen are trans, these two, and is cis-decalin. In cis-decalin, this is the view. In cis-decalin, these two hydrogen are cis, the two hydrogen atoms attached to the bridgehead carbon. It is written in this fashion. So in planar form, in two-dimensional form, these two hydrogens are written in the above of the plane bond, and these two hydrogens are written above the plane and below the plane bond. This is your trans-decalin and this is your cis-decalin. This one. Okay. Now, the same theory, the same principles are applied to the steroid chemistry also. In the steroids, look at here, these two fused systems are involved here. So, in steroids, this ring is actually A ring, this one is B ring, this one is ring C, this one is ring D. Likewise, this one is A, B, sorry, one hydrogen is there. One hydrogen is missing from here. This is hydrogen. A, this one is B, this one is C, and this one is D. Look at here. The junction of the A and B ring, the A and B rings are fused such a way that methyl and hydrogen are in cis position. And in this compound, the methyl and hydrogen are in trans position. So this is actually CAB fused in cis geometrical form, and these A and B rings are fused in the trans geometrical form. So these two are obviously geometrical isomers. This is a steroid system. These are steroids. These are steroids. In this compound, A and B are in cis fusion. A and B cis. And in this molecule, A and B ring, A and B rings definitely. A and B rings are trans. This is all about geometrical isomerism in fused ring systems. Thank you. Thanks a lot for watching the video.